Today, Professor Babak Modami is going to give a talk on interval exchanges, polygons, and moduli spaces.
Thanks the organizers of the meeting, also the participants for showing up. I mean, this is at 8 p.m. So I think I'm going to talk about some a topic which is remotely related to my research. I'm a geometer, and today I'm going to talk about a question in dynamics and how geometry can help us to address this question. So, and just right now, is everything okay? Can everybody hear me? And
yes, it's fine.
Right. Okay. So also during the talk, feel free to ask questions. So also I've been told that I have 1 hour, so we'll see how much actually I'm going to need. So in the title of my talk, there are three different names. So which as I'm going to go through my talk, probably we'll see what do I mean by those. So as I told you, so I wanted to discuss a question which is considered to be a basic question in dynamics. So, and it's about interval exchanges. So that's the first thing which you see in the title of the talk. But what are interval exchanges? So let me just draw a picture. So let's take an interval with, let's say, length 1. And divide it to a number of sub-intervals. Okay, so I'm going to divide, for example, this interval to 4 sub-intervals. So which are going to look like, so let's say this is the first one. So I have a slightly longer interval here, another one which is short here, and let's say we have the last one, okay? So now I have 3, and so let's make it also slightly longer. So this is, and let's make this come all the way here. So I, let's say, as I said, so just think about it, that I have this interval length 1, and I'm dividing it to 4 sub-intervals. So this is then at least the name the interval is obviously came when I was I did this division of the interval to sub-intervals. But well, what do we mean by exchange? So let's say I have so I label this interval. So let's say this is interval 1, sub-interval 1, sub-interval 2, 3, and 4. And I'm going to just say that, okay, so I wanted to send the first interval to the second position, the second interval to the, let's say, 4th position, the 3rd interval to the 1st position, and the 4th interval to the 3rd position. So this is going to tell us how to exchange this the intervals which we see in the picture. So let's say after applying this t, so I have the 3rd interval comes to the 1st position. So first I see this little interval which is 3. Then so the 1st interval goes to the, so these arrows tell me where to send each interval. The 1st interval is supposed to go to the 2nd position. So it's going to be here. Okay. So then the 4th interval comes to the 3rd position. So I have the 4th interval which comes to the fourth position, the fourth interval which comes to the fourth position. So let me just put it here. And finally, the second interval was supposed to go to the fourth position. So let's send it to there. So I have this. So as you see, so I get again the same interval, but this sub-intervals has been exchanged. And this is an interval exchange, which or we usually call it an interval exchange map, because you can think about it as a map from the interval of length 1 to itself, but just exchanging this sub-intervals. So, and this is an example of a dynamical system. So this is an example of, so let me write it here. This is an example of a dynamical system where we are just very interested to just keep iterating T and see what happens eventually. For example, so I'm going to tell you what are some questions which we can ask about what happens, but in particular, you can just pick a point, let's say somewhere along this interval. So let's say here, and just so let's say when I apply this T once, it's going to come here. So again, so I can just according to this recipe which I have, again exchange the intervals. Again, I see that the first the interval which is in the first place, so its label is 3, is going to supposed to move to the second position, and again the interval which is in the second interval in this new arrangement of intervals is going to be supposed to be sent to the fourth position, the third interval to the first position, and so on. So then again, we can just exchange or rearrange these intervals according to the recipe and keep doing this. So, so let me write it here. Just we want to iterate T and see what happens eventually. Okay, so also in dynamical systems, usually people are interested in some simple procedures like this, the interval exchange, which I explained. And as I said, just then they want to see when we iterate them, what happens eventually. And just maybe this particular question in the dynamical systems may seem to be a little bit abstract, but there are many examples of dynamical systems which are which appear in the let's say real life. For example, and for example, when you want to study what happens when you're watching, for example, the let's say a particular part of Earth and see monitoring the weather there. So that's also an example of a dynamical system, which is certainly, and some of the even the questions which are I mean related to this more practical questions can be reduced to questions about more abstract dynamical systems where you have a very much simpler and more concrete procedure, and you want to see what, as I said, so study them as you keep iterating or as the system evolves with time. Okay.
I have a question. Is this only for the straight line, or can you do this for any curve?
Like so right now we just do it for let's say an interval of length 1. So So the more complicated curves, well, I mean, at least, I mean, probably you could do it, but I'm not sure, first of all, that produces something which is new or interesting. And this is already quite complicated, and somehow, although I mean, sort of the system is very simple, so you just keep rearranging these intervals, but when you keep doing that, everything I mean, quickly becomes very complicated, especially keeping track of what's happening.
Thank you, Professor.
Okay, you're welcome. So now that we have just an intro, so is there any question about just the setup of this problem? Also, you can think about any other number of subdivisions and any other recipe for rearranging them. Okay, so for concreteness, I just wrote this example. Well, okay, so now let's see. So we have this thing that what happens eventually, but let's make that slightly more precise. So let's see what we can ask about things which describe I mean, what happens for these intervals as we keep iterating this rearrangement. So one of the things which comes up is that is this interval exchange map? So I'm just going to also just refer to interval exchange for the rest of my talk. Is it minimal? So and what do we I mean by minimal? So let me again just draw my interval. So it was so let's say it looks like this, going all the way here, and so let's say that the sub-interval, this, sorry, this and this. Okay, so this was my interval and its division. So let's say well, what do we mean by saying when we say that this is T minimal or not? It means that when I let's say pick up any point, so and I keep iterating T, so which means that I rearrange the intervals according to the recipe and watch what happens for my point. So also let me keep track of the time. Okay, so and when we watch it, so it's going to be minimal if this point and its iterates visits everywhere along this interval. In other words, if I pick any, let's say, part of this interval which is visible, so let's say some subsegment like this, there is some iterate of T. So let's say that this is I have this, and when the first iteration takes the second, remember it was taking the, so also I have something is wrong with my labels. So this was the last one was 2. So I have, this is 2. So then this thing here goes here. So in the first iteration, it essentially comes here. It comes inside the interval. But if I, for example, pick some other piece of this, let's say here, so then the first iterate is not there. So then the question is that if I keep iterating this interval exchange, does this point eventually land inside that or not? If that happens, we say that this dynamical system, which is just the iterates of the interval exchange map, is minimal. So let me just write here that the iterates of a point eventually visits every portion of the interval. That's what I mean by when I say that this interval exchange map is minimal. So I hope everybody agrees that that's the natural thing to ask. So it's just also it somehow measures how complicated it is. So it means that when you pick any point eventually, and you keep iterating this interval, you are not going to miss any piece of the interval. You are going to hit every piece. Okay, so it means that it's somehow shuffles everything. So another thing which one might ask about this dynamical systems, and also these two, the first this minimality and what I'm going to say in a moment, these are quite general notions which you can ask for any other dynamical system, which I mean you might visit later on. So one can also ask whether it's ergodic with respect to a measure. So here already I put a couple of words. First of all, a measure on this interval is going to be anything which looks like length. So let's say any thing which looks like length. So let's say for this interval, I can take any piece and measure the length, right? So the length of any piece is going to be positive. And when we put two pieces together, their lengths are going to add up. So and the length of the union of two pieces is going to be just the sum of the lengths of each piece. And the measure is something which looks like that. So to any piece assigns a positive number, and it has this additivity property. Okay, so is that good for everybody, or so? Yeah. So anything which looks like length is called a measure. So and it's not surprising that you can put the different measures even on this single interval. So and now the ergodic. So let me just write it here. So this means that no piece with so ergodic. So as we said, with respect to a measure. So let me actually, so this is going to be for everything. So ergodic with respect to a given measure. So we can also even give a name to our measure. So let's call it M. So with a positive measure is so no piece with a positive measure, which is not the whole interval. So here is a little bit of lie, but so is not is invariant. So in other words, we cannot find any piece of this interval which has a positive measure. So which is kind of, you can say that is visible with respect to it has positive length. which is invariant, unless it's the whole interval. Okay, so that's the meaning of the when we say that this interval exchange in ergodic with respect to some particular measure. It means that if you have a piece with which is visible, which has positive measure, and it's invariant, it should be the whole interval.
What
Okay.
Is there any like infinitesimal subset, like I don't know, like infinitesimally small piece that is invariant?
So yeah, so again, you need to say what do you mean by infinitesimal. So as soon as so you're so no matter so let's say if you think about the length, you can think about pieces which are very small, but still they have some length, right? For example, its length could be 1/10,000, but it still has some length, and even those things cannot be invariant. So they should be this map moves them, right? So invariance means that they don't move. And when it's not invariant, it means that it's this map just moves that piece. Okay, so as soon as it's visible by our measure, so it's has positive measure, it's gonna move under T when we have this ergodicity. Okay, so also I hope that's at least. I gave the sort of these are two conditions which two, let's say, notions which somehow describe the give complexity of the system, and also let's say also it iterates. Okay, so and here there is another thing which I want to say. So there are going to be a couple of notions at the beginning. So this, first of all, before going there, this ergodicity, I'm going to write something which is highly non-trivial, but essentially follows from the definition. So if you're patient enough and work with the definition, you can see that that follows. So, and which is the following. So if you keep iterate this, so let's pick, so if we pick part of this interval, so let me just again draw it here. So let me see how long is it. So let's say if you take this interval and take some sub-interval of it, so let's say a piece which looks like this. So, and then now just keep iterating these exchanges and watch what happens for a point. So we had this point which was here, and we saw that it lands here, and so on. So we can just keep iterating the interval exchange and watch what happens for this point. But there is something which follows from this ergodicity, which again ties the dynamical system, which is just the iterates of this interval exchange map, and the measure, which is the system is supposed to be ergodic with respect to that, is the following. That essentially tells that the size of this interval, let's call it J. So the size of this J, which comes from our measure, is going to be comparable with the number of times, or the average of the times that this iterates of the point, this red point, hits that. So to make it more precise, I just write what's in terms of formulas. So so the number of the i's such that ti, so ti means just is the ith iterate of t. So I do it once, then twice, three times, and so on. And I just means the ith iterate of the interval exchange. for the given point. So let's call it, let's say this is my, this, so let's use the red color for this. X intersection with J. So, and this I should be also, sorry, this is I less than or equal to N. So is going to converge to Mj as N goes to infinity. So this is just writing what I said in the mathematical terms. So it says that, so just fix an N. So this N is a big integer, let's say 1000. And see when you go up to 1000, so when you iterate this interval exchange map 1000 times, how many times you hit J. So when Tix intersecting J means that how many times the iterates of X intersecting this small interval J and divide that by N. So this is somehow is the average of the number of times which you hit this small sub-interval when you wait until end iterate of this procedure. That goes this average converges goes to, so these are all numbers, and these numbers are going to converge to just a measure of this set. And this happens only when this dynamical system T, this interval exchange map T is ergodic with respect to the measure N. So this is just correct for these things. As I said, so this is a non-trivial fact, but which is correct, and is a characterization of ergodic measures of a way of characterizing ergodic measures for certain dynamical system, in this case for this interval exchange map. Okay, so we had this. So let me also put the last general nonsense thing which I want to discuss. So then there is this thing which is called uniquely ergodic. Uniquely ergodic. So then my system, or in this case, this interval exchange map is uniquely ergodic if there is, so let me with this, there is only one ergodic measure for T, this interval exchange map. So because I said that you can come up with different measures, and as soon as either of, so what we said, that the only invariant visible subsets are the only invariant visible subset is the whole interval. That was the notion of ergodicity, or what we mean by a system being ergodic with respect to a measure. Or you can think about this other reformulation of that. So starting from this interval exchange map, you can just imagine that you have the different measures which such that this system is ergodic with respect to those. But unique ergodicity means that there's only one. There's one and only one measure which such that the system is ergodic with respect to that. Okay, so and this is also a fundamental notion in dynamical systems, and I think that this is the whole maybe some a few notions which I wanted to say at the beginning of my talk. So, which I actually right. So we are almost in the middle of the talk. So first of all, are there any questions or Maybe is it too much of information for the beginning or not? So everybody is okay. So I think that you have the feeling that these are kind of relevant and show how somehow measure the complexity of the system. Is that correct, or maybe is there any objection or?
I think it's good.
Okay. Okay, so now let's move on, and let me just write this this main theorem or fact which we want. I hope to be able to say that the rest of the talk is going to be more hand waving. So which is the main result which I want to tell you, and it actually is due to Mazur and Rich. So these are two mathematicians. Mazur is still alive. He's in the University of Chicago, and Rich unfortunately passed away a couple of years ago. So this is a result from the 80s. So so we're getting to the, let's say, these are not quite antique results. So kind of it's happened in the 80s. That and by the way, this interval exchange map themselves, there has been probably around, people has been studying them for maybe a century or something like that. And this is a result from the 80s, which says that almost every, so let me just use the interval exchange map or transformation is minimal and uniquely ergodic. For uniquely ergodic, also I'm just I'm going to abbreviate that. So which means that so as we saw, so both minimality and the unique ergodicity are ways of to measure the complexity of the system. And so this says that again, so I don't want to get into the details that what precisely almost every means here, but it means that for so if you start with an interval and just divide it to a number of pieces and write a way of or you have a recipe for rearranging them, then unless you're unlucky, what you the interval exchange map which you produce is going to be minimal and unique ergodic, which means that it's complex. So let's call it that it's complex. In terms of as a dynamical systems is something interesting. For example, the orbit of every point, or when you iterate, you pick a point and you just iterate the interval exchange map, it's going to be to visit essentially everywhere on the interval. Okay, so now that we have, I also told you what's the main thing which we want to discuss today. So let's also another point of this talk is to show that how we can use more geometric methods or to study this dynamical systems. So as maybe as you also realize, so when I was setting up this interval exchange and giving you this definition and so on, it was so there was the feeling that everything is slightly boring. So I was just giving you definitions and so on. But there is so by adding some structure to this picture, so a priori this is just an interval divided and keep rearranging. But by adding some more structure to this story, we can actually address the question, which makes it actually even slightly more interesting. You can see more interesting pictures and so on. So let me tell you why. So let's look at the interval exchange which we have here, and I'm going to draw a polygon which sort of contains my interval exchange. So let's look at this part. So, and let me use let me use the color blue. Okay, so let's say I have something which looks like this. So it comes up here, then here. So then it comes to here, and then comes down here. Okay, so let's also show these pieces. So this is one of the segments. So these are going to be the sides of my polygon. So we have this. So now let me just use this and this. Okay, so having this, and then I'm going to just continue to close it up. So I'm just going to have the parallels to the segments which we already saw. So we have something which looks like this here. Okay, so then a little bit here. So this is going to be parallel to the other, to that side. And so we have something which here, which comes here. So this is parallel to this, and eventually we close it up like this. So now, as you see, we have this polygon, and this my interval is just a segment inside the interval. But the point is that we can just realize our interval exchange by doing a vertical flow in this picture. So let's see how can draw that. So it means that I just, for example, I start from here, I come up here. So then I just find the corresponding point here. So, and sure, my picture is not quite the one which is supposed to be, but let's, so. And then let's say this comes all the way up here. And then we also remember, so we identified, we're supposed to identify the sides which are parallel and are labeled with the same symbols. So, and then now this is going to be identified with this, and maybe it comes somewhere here, which is so as you see. So this the way we moved around and came back looks like that we shifted this. So this point has been shifted slightly to ahead, which means which essentially. So if you look at the interval exchange on the right-hand side, you can see that we were supposed to insert the third interval to the first position, and the first interval was shifted to the slightly to the right-hand side and appeared in the second position, which this picture does that for us. And you can also pick other points. For example, a point, let's say here. So this is the second interval. It's supposed to be identified with something here, and let's say eventually lands maybe somewhere here. So which again, so you can see that when we come back, so this is second interval was supposed to go to the end, and this also shows that this is a point which appears toward the end of interval, to the where this second interval was moved to the fourth position. So, and this is so this is how polygons come into the picture. So we can use them to realize this T. So let me write it maybe here, that T. So, and what we did right now, so just a flow, doing vertical flow and vertical flow in the picture, and just again, just coming back to the interval for the first time, that this T is the first return map of the vertical flow. Also by vertical flow, I mean that for any point we just take the vertical direction and just follow it until we hit a side of the polygon, and then we see where we are supposed to come back in the polygon based on the way the size has been identified. Of the vertical flow on the polygon. Okay, so how much do I have actually from now? Right now I have another 20 minutes, right? Yep. Okay, so now that we have this picture, so probably I need to move slightly faster. So we have these pictures, and I told you how the interval exchange map fits into this polygon picture. And remember that, so let me move that this polygon was a polygon where with some side identification. So when we do the side identifications, we get a surface, right? So this polygon already is a surface, but it's part of the plane. But then when we do the side identifications, we get a surface which is more complicated. Actually, in this cases, we are going to get after making these identifications, we are going to get a surface which has genus 2, and all of the corners of this polygon are going to be identified to give us a cone point. So this is a cone point on the surface. Also, since so we obtain this surface by identifying the size of the polygon. Every piece of this polygon, every piece of this surface looks like a piece of the polygon. So it's I can just, if we think about this polygon with its let's say let me use this other color, this vertical, and let's use the color red, horizontal coordinates, so in the of the plane, so which gives us the vertical and horizontal directions. So they're also going to show immediately on this plane, so on this surface. So I have everywhere. So it's I have wherever on the surface I look, it's going to look like a piece of the polygon with this pair of horizontal and vertical curves which come from the horizontal and vertical directions in the plane. So, and this is called, this whole thing is called a flat surface. So this is a flat surface with cone singularities. So which we got from this trying to think about the interval exchange map as the first written map of this vertical flow on the polygon. So, and let me tell you also a little bit about this flat surfaces. That for each one of these ones, these surfaces, for example, we can first think about the injectivity radius. So let me write it here. Radius of the surface, so let's call it x, which is the length of the shortest loop on the surface. So when you look at this, for example, maybe this is a loop. So you go around the handle of this surface. And so when you look around, you can convince that this is probably the shortest one. And the length of that is called the injectivity radius of this surface. So this is something which describes the geometry of this surface. For example, how pinched is the surface, or so maybe that's the measure of that. And another thing which I want to say is that the space of this, if I take all the polygons or all these surfaces, so they form a space, so which is called the moduli space. So let's consider the moduli space of polygons, or we can say flat surfaces. So this has a finite volume. So in other words, there is a way of assigning volume to this space. So the space of all of this. So now up to this point, we talked about just one polygon, but you can think about all different polygons, which where the corresponding surface has genus 2. So it's a surface which looks like this. And when you put all of them together, that's called the moduli space of polygons of certain type, or flat surfaces of certain type. And it has a finite volume. And one way to describe this volume is just think about the size of the polygon. So there are vectors in the plane. Also, if I hope you've heard of also we have on the plane we have just we can refer it as the complex plane, where instead of let's say x and y, we have the way of labeling them by just a single complex number. And when we think about this vectors, this sides, they give us a bunch of complex numbers, which says that we can just put this space of polygons in some Euclidean space, some space which is just the product of this the planes. So let's just keep it also that way. And then the volume is just going to be the volume which we see there. So that's the way of assigning the volume. And the interesting part is that this space has a finite volume after the volume which is defined in this way. So so now that we have I discussed all these things. So let me see. So sorry. Okay, so let me also tell you, I mean, I'm not sure if I get enough time to get into more details, but there is, so now that we have this space, there is also a way of deforming these polygons, or these flat surfaces. So let's say I start with this, my flat surface with this pair of curves, the horizontal and vertical ones, which come from the polygon. So then there is this thing which is called the Titular Flow, or Titular which is a way of deforming these surfaces, and actually it's has a very straightforward description in terms of this pair of curves which we saw. So let's say I have a piece which looks like this, and so let me just end this. So this is a piece of the surface with so then the titular flow is going to just stretch it vertically and contract it. Stretch it horizontally and contract it vertically. So it's going to take this to something which looks like this. These red ones are going to get further from each other, and the other ones get even closer to each other, the horizontal ones. And this is what the titular flow does locally on this surface. And then when we patch these things back, we get a deformation of our surface. Okay, so this is let's call it. And so let me just. This is let's call it GT. So which is the titular flow, and it's usually shown by so we, as we said, we stretch and contract with same factors which are going to just look like applying this diagonal matrix to these things. So, and there are a couple of facts about this. First of all, this GT preserves the volume of the moduli space, which is just the space of all these flat surfaces. So this is a very crucial property of that. So now I need to tell you another fact about this flows. So this is sometimes called the Poincaré recurrence, so which is the famous Poincaré recurrence theorem. Actually, so which says that almost every, so again we have this word almost every titular flow line. So which means that I just take a surface and apply this to that line is recurrent to the parts of moduli space where this injectivity radius, which I told you, which is the length of the shortest loop on the surface, is bounded below. Okay, so let me also, so here there is this word, so let me actually draw a picture and explain about what does this say. So let's say, so this is the picture for my moduli space. So let me also show it by M. Okay, so we put all this flat surfaces together, and we get something which is itself is a space of where every point is just a flat surface. And let me just show it by something which, I mean, like this. Every point here represents a surface. So, and this part where the injectivity radius is bounded below is going to be a piece of it, which looks like this. And now this recurrence theorem tells us that if I pick any point, so let's say if I pick a point maybe here, this is going to eventually, it's going to be the flow line which passes through this, which starts from this, is going to be recurrent to this part, which means that it's going to visit it. And and recurrence means that visits this part infinitely often. So it means that there is an infinite sequence of the times where this ray intersects this part. So let's me just say that means that it means that infinite visits infinitely often. Okay. So now having this, so right now, I mean, as you saw, so maybe, so we started from this interval exchange map, which was this boring way of rearranging intervals, but and a priori, and I told you about some basic notions or concepts about the complexity of dynamical system, and in particular, in this case, this interval exchange map, which was minimality and unique ergodicity. But later I switched and we did quite a bit of geometry. We got this polygons, surfaces, and I told you take this flow on this space of surfaces or polygons and look at the part where these surfaces are somehow thick. Their injectivity radius is at least is bounded below. And I stated this thing, and sort of this last part was quite a bit of geometry. So we developed more and more structures. So, and the hope was to apply all of these things to answer to address that thing which we wrote initially about interval exchange maps, that almost all of them are minimal and uniquely ergodic, or almost all of them are complicated, and that essentially follows from this Poincare recurrence theorem, which actually is a very easy fact. So, and you just need to think that if this ray doesn't come back to this part, so you can just have a piece of this space which is going to move away from itself, and somehow so if it's never intersects itself or comes back, it's going to patch. You have a patching for this space with a number of pieces which makes the volume of this thing infinity, because you have all these patches which are disjoint from each other, and they're in this space. So, and each one of them has some volume, and together they're going to make the volume of this space infinity. So then the assumption that this space has a finite volume forces the things to intersect each other, which means that we get this recurrence. So this was a very kind of general way of some sort of sketchy way of saying that, well, why is it correct? So, but now let me tell you just in the last few minutes. So I hope I can just wrap this up. That how this. So as I said, so this thing which we said about interval exchange maps is going to follow from this. So we need to do a little bit more work. So, and here there is this thing that this is again a theorem which is due to Mazur. It's part of his proof from the 80s that. So if you have a recurrent ray, and this is the recurrent Titular Flow line or recurrent Titular Flow ray, which is recurrent. So let me write it that the recurrence of Titular Flow line implies that implies the unique ergodicity. Okay, so, and the way to prove this is so let me just put some steps. So we've proved the contrapositive of this. So the contrapositive of the statement is that if you have so polygon interval exchange map with the polygon, which gives you also a surface which is non-uniquely ergodic. So this is just going to be the contrapositive of the statement. This implies that the flow line is divergent. But divergent also here, we just mean that it's not recurrent, which means that the injectivity radius along this ray goes to 0 as t goes to infinity. So I think I'm out of the time. So can I have another maybe 4 minutes? Or
Yeah,
everybody is completely bored, or?
Yeah, I think that's fine. Another few minutes.
Okay, sorry. So because of so I'm going to just quickly tell you, and you're going to enjoy that. So it's I just want to say that how this flow and the way this contraction expansion, which we said, actually comes to play the role. So that then, to prove such a thing, so suppose that this is not correct. Suppose not. So this is not correct. Then there is GT, which is recurrent. So not non-being divergent, which is recurrent, is recurrent. So recurrent also means recurrent to a part where the injectivity radius is bounded below and is uniquely ergodic. The interval exchange map, which we see is uniquely, which we see as the first return map on the individual surface, is uniquely ergodic. So let's see how we can get a contradiction, how having such a flow line is going to produce a contradiction. This is going to use quite a bit this the picture of the titular flow and this other formulation of the ergodicity. So if we have something which is non-uniquely ergodic, it means that there are two ergodic measures. So let's say, let's call them M1 and M2. And there is a sub-interval such that these two are not equal to each other. So this is what non-unique ergodicity means. Okay. So to see this, so let's see why this is going to produce a contradiction. So let's take, remember, so this is again, we're getting back to this interval exchange picture. So this is my interval, and let's say that there is this sub-interval. So let me label it by J. Okay. So which has and I have this two different measures, and I said that this is the two different ways of assigning lengths essentially to sub-intervals where these two are not equal to each other. So then by this other way of saying non-unique ergodicity, sorry. So if there are points, so let's say one of them, so they could be also even inside here. So let's say I have a point x1, so and a point x2, such that when we look at this average which we wrote, so this, so I'm going to write it in a slightly different way. The t is smaller than t, such that GT x1 intersection with J, this is non-empty. So remember, this was supposed to go to M1, and so because T is ergodic with respect to M1, and then we had also this others, it's the same essentially average for maybe some other points. which is supposed to go to this other measure. But now is where, so this is the most the geometric part of the story, which makes everything interesting. So let's take a piece of this picture. So let me just so let's say I have J. I take let's say a small piece of so this is going to, remember, this interval exchange is inside a polygon. So remember, so we had this polygon which was around my picture. So let's actually just anyway. So I just drew part of it somehow. And so this is the picture, and let's say it's so we had a way to kind of complete the whole picture, right? So we have this is parallel to this, and so on. So this is already inside this polygon, and this polygon had identifications and so on. So now let's take piece of this polygon, which is here, and and this. I have this. Sorry, also here I meant to write. So let's say this is the vertical flow on the surface. So let's call it. So I have phi here and phi here. This is the vertical flow on the surface. So this is from the non-unique ergodicity. So now I want you to apply the titular flow, which is somehow perpendicular to this vertical flow on the surface. And remember, so this is going to take my picture and stretch it quite a bit. So let's say I have my x1, which is going to be here. X2 is going to be here. And this box which we had, so this is going to, so this was the, let's say, the lower part of it, which is here. And so so this is also going to kind of get, go everywhere around the surface. So I have this, and so then, so let me just actually have this, this, and this. So then, in particular, this part is going to be stretched in this my surface, which is still is this it's supposed to be my surface with whose area is fixed. So this is going to be quite a bit kind of wind around in the surface, and this lower punch is going to come above and intersect it despite quite a bit, a lot of times. Okay, so and now the point is that and let's say these are also this recurrence times which we had. So we have this direction by the Poincare recurrence is going to recur to this thick part. Let's say infinitely often, and these are, so I'm just taking this snapshots at this recurrence times. So now these two averages which I wrote here, these are corresponding, so as we said, so it corresponds to the vertical flow and flowing for a long time on the surface, and see what where does these things go. And this average just sees how many times this vertical flow, let's say in the first one starting from x1 and going around the surface intersects into this interval, and the second one tells us the one starting from x2 after a long time how many times intersects that interval, and then we just average that, and let t goes to infinity, and we get the measures. So, but now this titular flow takes this this is small segment, this small vertical size of this box to this very long things, but the vertical flows become very, very short. And now here you can see that when we look at this picture, it's clear that this green horizontal flow intersects both of this short vertical things in almost essentially the same number of times. Okay, so which means that these two numbers which we wrote here, so let me just show it. These two are essentially the same. So looking at the intersection of this the orange thing with my interval in this picture, so which was so is the same as seeing again counting the number of intersections of again the green thing with the orange in the second picture. But in the second picture, everything was under control. So I have this. I see this triangle which with vertical side lengths which are short, and the other thing is just keeps going inside it, and they intersect both of them with the same number of times. Which means that these two numbers which I have on the top and bottom are essentially the same. So now when t when set t going to 0, we get the same numbers or measures for this interval, which contradicts the fact that we said that these two measures assign to different numbers to the interval. And that essentially finishes, so it's a contradiction for having a recurrent rate with a uniquely ergodic interval exchange corresponding to a uniquely ergodic interval exchange map, which so essentially tells us that so now from this the major the theorem which I told you is obvious, because this almost every direction in the moduli space is recurrent, so almost every interval exchange map which appears as the first return map of the vertical flow is going to be uniquely ergodic. And so I know that I went quite a bit, I mean, after the time which I was supposed, but I just pushed it to kind of to get to the point that to see at least maybe vaguely how this whole geometric picture and doing this flow on the modular space and polygons actually is going to produce something useful about the original problem, which was very, I mean, it was simple, but there wasn't enough tool or enough kind of room to work with that, with just the interval exchange. But when we moved to the world of polygons and we said that what's the titular flow and so on, so suddenly we got quite a bit of room to, we could talk about the volume of this space of polygons and so on. So that gave us quite a bit of room to actually to address this very rigid problem. So, and I'm almost done. So unless there are questions, I was hoping to get more questions during the talk, but.
Yeah, so does anybody have any questions about the talk?
So about like the recurrence for the interval exchange maps. Am I right?
Recurrence theorem, or
Yeah, is it you're saying it's almost guaranteed to recur, basically, right?
Yeah, as long as the space is finite volume and this flow which we have preserves the volume. So remember, so those are actually I told you those were the properties. First of all, the titular flow, I told you, it preserves this volume of the space of polygons. And the space of polygons has finite volume with the, or maybe surfaces has finite volume with respect to that. Yeah, as soon as you have these two things, it's going to follow. So it's a very general fact. So when you have
Then I have a follow-up on that. So basically, you're also saying that the measure of like how ergodic it is, that also determines how long it will take to recur. Is that right?
no, here ergodicity doesn't play any role.
Oh, okay.
So just finite volume and the fact that this flow preserves. So now we are in different worlds. So we're in the world of surfaces with titular flow on them. When I was talking about ergodicity, we were in this the world of interval exchanges and let's say measures.
Oh, okay. I guess I was confusing them. So that I think that clears a lot of things up.
Yeah, you're welcome. So I guess that's the whole thing. So we have these two words, so interval exchanges and surfaces and the space of surfaces. So then by polygons we bridge between them, and then use this quite a bit of geometry which is available on the space of flat surfaces. And I told you that we can define volume for them, and we can do titular flow by just contracting and expanding these surfaces along these two particular directions, or in terms of these two particular families of curves. Then suddenly we have quite a bit of room to work.
So thank you very much.
You're welcome.
So you have like you said that this Teichmüller flow, you have something, is this like Hamiltonian? Because you have, I guess, pretty much like Liouville's theorem for a Hamiltonian system to have.
Yes, and sort of this is, but again, so on the marginalized space, there is let's say to be Hamiltonian, so you need also a symplectic form, right? So on the moduli space of the Riemann surfaces, let me see. So it certainly preserves the volume. But again, so to say that whether it's a Hamiltonian, you need to give me your maybe symplectic structure, which, well, actually, I doubt that Teichmüller flow. There is this other thing called Weil-Petersson flow. That's Hamiltonian with respect to some natural symplectic structure on the modular space. But I don't think that Teichmüller flow preserves that. Anyway, so we need to talk about. So first, you need to tell me what's your symplectic form, and then I can think about whether it's going to be preserved and whether the system is Hamiltonian or not. Yeah,
I don't know, like a natural.
Yeah, that's a good question. But anyway, so I didn't use that, but sort of yeah, that was a good question. But I'm saying that not this one, I should say. So that there's some other kind of let's say metric and volume structure on the modular space where there you can say that the geodesic flow is Hamiltonian, but here this is, I mean, I don't think that that's correct for this.
What's the symplectic structure on the moduli space?
That's I mean, takes us a little bit away from this world of right now. I talked about the flat structures. But if you think about there is the hyperbolic structures on surfaces, there is the Fenchel-Nielsen coordinate, and in those coordinates you can put you can define a symplectic structure, which anyway, or maybe anyway. So that's a bit I mean not super related to what I've been talking about.
Isn't Fenchel-Nielsen just for Teichmüller space, not for moduli space?
Yeah, that's also correct. So, but when you have the thing on the Teichmüller space, it descends to, so you put the Fenchel-Nielsen coordinate, you define the symplectic form, but then it descends to the modular space.
Oh, so you're talking about the symplectic structure on like MG, right? Not HG?
Okay, so yeah, these are also, I put everything under no, the symplectic structure is also going to be on MG, but HG, I think you're referring to this, the various strata of the moduli space, which again, so that would be related to this flat world. And in the flat world, I don't think that there is a symplectic structure as far as I know. So things which are tied to this flat, to titular flow, and this polygons and the flat things, there is not much of symplectic geometry. But when you go to the hyperbolic world, think about hyperbolic structures on the surfaces, and there the Fenchel-Nielsen makes sense, and you can think about the there is this symplectic structure, and there is also Weypeter metric, which is somehow compatible with that symplectic structure. But again, so these are different structures on the moduli space, and so also the moduli spaces which we are talking about are slightly different. So this how we are talking about modulus of flat surfaces, there you need to think about moduli space of hyperbolic surfaces. Is that good, or maybe, I mean, I don't know, so we need to so for I mean, publicly probably it's not useful to kind of, but later on we can just talk and see how far we can talk about that.
Yeah, thank you.